All right, so this problem here, we have an astronaut in a spaceship, and you can't really see it, but he's standing on a scale. He's standing down there on a scale. In this problem, the first question is, how heavy is the astronaut before he leaves, before the spaceship blasts off? In other words, when the spaceship is on the Earth, how heavy is the guy, is the question. Well, you got to simply find the force of gravity acting on him. All right? So the question is, how heavy is he? Let's take a look at that. All right. So the free body diagram of the guy. The guy is the system here. You guys know what a system is. The free body diagram, and again, this is, as an astronaut, he hasn't left yet. He's just sitting there on the ground, okay? The rocket has not taken off. At this moment, he has two forces. He has a normal force, and he has a force of gravity. Remember, the normal force in this case is simply preventing him from falling through the ground. Okay, it's not making him lift off. And it's not making him go through the earth. All right? So, we're looking for the normal force. The normal force is the force of the scale pushing him up. But because he's not moving yet, because he's still on the earth, there's no net acceleration. When we write our net force equation, and again, this is problem A, the net force is equal to the normal force minus the force of gravity. But if he's not moving yet, if the spaceship is just sitting there still, the net force is going to be 0 newtons. Equals the normal force, which is unknown yet, minus the force of gravity. The force of gravity is mass times 9.81. So we have 0 newtons for net force equals normal force minus the mass of the astronaut, which is 80 kilograms, times 9.81 meters per second squared. And again, I made it positive because I already accounted for the negative here and here and here. So we have 80 times 9.81. 0 newtons equals normal force minus 80 times 9.81, which comes out to be, very good, 784.8 newtons. Yes, what's your question? Okay, right. So this number represents the force of gravity pulling down, 784.8 newtons. And because there's no net force, then the normal force is going to be equal to the same thing. It's also going to be equal to 784.8 newtons. Yes, you may. Therefore, the normal force is equal to 784.8 newtons. And the scale then will read 784.8 newtons. Because the normal force is the scale pushing the guy. Any questions on that problem? Part A. You're just finding the normal force on the guy, the weight of the guy. This? Okay, because well, so you're asking why the normal force is 748, or? Right, well, if you, if you bring the 784.8 newtons on this side, the normal force would equal that. I mean, you have 784 newtons pulling down. How many newtons need to pull up in order for the sum to equal 0? Right, 784. Right, the sum is equal to 0. All right, let's do problem B, or part B. All right, so in this part here, now the guy has blasted off. So now he has a force pulling down, which we already figured out the force of gravity is 784.8 newtons. Okay, we've already reasoned that. But now he's accelerating upward. Good. So this force is the force that the scale is pushing up on him. The scale is getting pushed up by the floor. The floor is getting pushed up by the rocket. So really, the normal force in this problem is the force that the rocket is pushing up on him. But because the normal force is a scale, the scale is going to read whatever the normal force says. So we have some force minus some other force, and it's going to equal an unbalanced net force. So what's the net force equation going to look like? F net equals the normal force, which is the force of the scale pushing up on him, minus the force of gravity pulling down on him. Okay? And now we need to figure out each thing. The net force is going to equal the mass times the actual acceleration of the guy. And that's going to equal the unknown normal force minus the weight, which we already figured out, but I'll write it out just for the heck of it. So the net force is going to be 80 kilograms times the actual acceleration, which is 20, times 20 meters per second squared. And that's going to equal the normal force minus the mass of the guy, which is 80 kilograms, times 9.81. And I made it positive because I've already accounted for the direction with the negative there. So 80 times 20 is 16 with 2 zeros, newtons, equals the unknown force minus 748.8 newtons. So we have some force minus 748 equals 1,600. We now need to figure out that unknown force by adding them together. 1,600 newtons plus 784.8 newtons. Thank you very much. 2,384.8 is equal to the normal force, which is the force of the scale pushing up.
Can I borrow your loudspeaker?
All right, so here is your normal force. Okay, the normal force is the force pushing up. Let's redraw this a little bit better here. I want to show you guys what's going on.
So is that what you just, this is 238?
Yes, the 2,384 newtons is the force pushing up. Right. So let's look at this. So we have the normal force, which equals 2,384.8 newtons, plus, I guess I'll write minus the force of gravity, which is down. Oops, it's supposed to be a G. Force of gravity, which is 784.8 newtons, equals 1,600 newtons. Okay? I hope that makes sense to you. We have 2,000 newtons, 2,384 newtons going up, right? The scale is pushing him up, but gravity is pulling him down with 784, so the result is 1,600. But the thing is, when we solved this problem, this was unknown. This was unknown, so we had to say what minus 784 equaled 1,600. So all we did was we took 784 and we added it to 1,600, and we got 2,384. That's all we're doing here, okay? That's the point of doing a net force equation, is it?
So you didn't even need the mass of the spaceship?
Nope, the mass of the spaceship doesn't matter. The only thing that matters is that it's making him accelerate at 20 meters per second squared. Now the mass of the spaceship affects the acceleration of it, but since it's already given, it doesn't matter. Alrighty, so that was part B. That was a B. Part A was just finding out that its weight was 784. Part B was finding out the normal force as it was accelerating. All right, any questions on that? Part B, we doing all right? This is a big problem. All right, let's do C. And I think it gets a lot easier after this. Okay, so now part C says, how much thrust can the rocket engines produce? How much thrust can the rocket engines produce? All right. So now in part C, we're looking at the rocket as a whole. So now the rocket is going to be the system. So now we have a new free body diagram. We have the force of gravity on the rocket pulling down, minus this new force. What's this new force going to be called? What do you guys want to call it? Or where does it come from, that new force? What's the force that's pushing the rocket up? Right, it's the force from the rocket engine. You can call it F sub T. That's how they would do it in just basic engineering classes. Okay, so we have the thrust going up, the force of gravity going down. And we know that the force of the thrust, I'm going to scoot this over a little bit so we can do some better math. We know that the force of thrust minus the force of gravity is going to equal the net force. Okay, in this problem, which one are we looking for? The thrust force, the force of gravity, or the net force? We're looking for the thrust force. So this minus whatever the force of gravity equals will equal whatever the net force equals. So let's figure that out. So the net force, good, is m times a. You got it. And that is going to equal to the thrust force minus the gravity force. Okay, so you calculate the net force by taking the mass of the thing that's accelerating times its acceleration. And that's going to equal this unknown thrust force minus the force of gravity, which is the mass of the thing that's being pulled by gravity, times the acceleration of gravity. Okay, the mass of the spaceship is 15,000, it's huge, kilograms, times 9.81 meters per second squared. Oh, sorry. The acceleration is 20 meters per second squared. And that's going to equal the unknown thrust force minus 15,000 kilograms times 9.81 meters per second squared. All right, so we have the net force here. The net force is going to equal this huge number. 147,150? 150 newtons. Okay, so that's the net force here. So these are going to equal 147,150 newtons. Okay, what's
15,000 times 20?
yes?
I had 300.
Let's see. Okay, yeah, I think, let's see. Okay, yeah, so that's fine. That force is going to go. So this 15,000 times 20 is 300,000 newtons. It's okay. Equals the thrust force minus what he calculated as 147,150 newtons. So now we can put it in our picture here. So the sum of these two is going to equal 300,000 newtons. Force of gravity is equal to 147,150 newtons. Okay? So then what does Ft equal is the question. What minus 147,150 equals 300,000? Well, you simply you take this and you add it over here, right? Because it's a minus here, so when it comes over, you add it. So you get 300,000 plus 147,000, and you get 447,150 newtons. So that's how much the engine is pushing up with. 447,150 newtons. Okay, that's how much is going up, but gravity is taking away 147,150 newtons of it, leaving 300,000 newtons left to go. Any questions on that? Any questions? All right, moving on. Part D, and again, if you're missing any of this, it'll all be on the podcast. Except, let's see, Part D says, okay, what is the net force on the rocket? Well, didn't we already figure out the net force on the rocket? What's the net force? The net force on the rocket we already calculated is right here, 300,000. Okay? The net force equaled MA, which equaled all this stuff, which equaled this. So, you've already got the answer for Part D. Yes. Part E, the net force on the guy is going to equal M times A. The mass of the guy is 80 kilograms. And we've already calculated this. I'm just showing you how to do it. 80 kilograms. And you could do the same thing for Part D as well. Times the acceleration, 20 meters per second squared, equals 1,600 newtons. There's the net force on the guy. All right, any questions on that? All right, cool deal.